Yesterday afternoon, you looked at this formula, I believe, and discussed the various symmetries of the Riemann tensor. Now, just to remind you how we derive this formula, we showed you can always, so this is the general definition of the Riemann tensor, following from its definition as the commutator of two covariant derivatives acting on a vector. So you obtain this general definition. Notice it's obviously antisymmetric under mu goes to nu because it was defined as a commutator of grad mu, grad nu. But it's quite a mess in that form. If you expand all the gammas out in terms of G and the derivatives of G, it's quite a mess. So you can use a trick to understand its symmetries, which is to go to a coordinate system in which the metric is eta mu nu, plus, and then we have the second derivatives, mu nu rho lambda x rho x lambda, right? So we can always, this is the second derivatives evaluated at the point 0. So we proved we can always go to a local coordinate system in which the metric is flat, the first derivative vanishes, and the second derivatives we didn't manage to set 0. And then I told you that, in fact, the fact that you cannot set the second derivative 0 is encoded in a tensor. And if a tensor is non-zero in one coordinate system, it's non-zero in all coordinate systems. So, and this tensor is the Riemann tensor. So, we've constructed such a tensor out of the second derivatives. We can always go to this coordinate system at any point. We can choose that point as the origin, go to a coordinate system in which this is true, and then we can drop the first derivatives of the metric, right? So in such a coordinate system, so this is in locally flat coordinates, or locally Minkowski coordinates. G is this, and the first derivative of the metric is 0 at that point, and that, of course, implies that the connection at the point is 0, because the connection involves first derivatives of the metric. If they're all 0, the connection is 0. So then it's rather easy. These terms are obviously 0, but the derivative of gamma involves second derivatives of the metric. If you just use the usual formula, plug it in, you obtain this formula. And the point of this is, now that I know the Riemann tensor at the point 0, all these things are evaluated at 0, I can infer something about its symmetries. Okay, and then I think in class you should have convinced yourself that if I lower all the indices, sigma rho mu nu, this is, first of all, symmetric under exchange of the first pair and the second pair of indices. Okay, so if I just flip, so this is equal to R mu nu sigma rho. Secondly, antisymmetric on the first pair and second pair of indices. So that just means it equals minus r rho sigma mu nu, and it's also equals to minus r sigma rho nu mu. So it's antisymmetric under exchanging the first two indices or the last two indices. And thirdly, it is cyclic in the last three indices. So we have this equation, r sigma rho mu nu plus r sigma mu nu rho plus r sigma nu rho mu. And then using these symmetries, in fact, you can prove, and I'll leave this as an exercise if you're interested, if you have an idle moment, which I doubt, but if you do, you can prove that that the Riemann tensor r sigma rho mu nu has d squared minus 1 over 12 independent components. Okay, so a tensor with these symmetries doesn't have, naively, this would have d to the fourth components in d dimensions. It doesn't have d to the fourth, it has much less than that because of these symmetries. And if you remember, which you probably don't, but if you do remember, this is exactly the number of second derivatives we were not allowed to set 0 by coordinate transformations. So the circle closes. This Riemann tensor really is the description of curvature of the space-time in terms of second derivatives of the metric. Okay, so now we will continue. So I think I used one of these symmetries yesterday. I used the fact that Riemann was antisymmetric on the first pair and the second pair of indices. So if you remember, yesterday we tried to follow Einstein, and we argued that the only sensible equation, the only equation involving two derivatives of the metric and relating that to the stress energy had to take this form where x mu nu is constructed from the metric and the covariant divergence of x mu nu was 0. Okay, and then we had some discussion about this. Did I really have to insist on this? Because maybe I shouldn't consider the most general possible metric. But we do want the most general possible matter in the theory, because you can make an awful lot of different kinds of distribution of matter. And we want this equation to be valid for any of them. And so it's very artificial to impose any additional constraint on the metric. Okay, so this is what Einstein was looking for. And the constant is not yet determined. And then we saw that the candidate for x mu nu is G mu nu, the Einstein tensor, which is the Ricci tensor minus a half G mu nu times the Ricci scalar. And the reason is that this identically obeys d mu G mu nu equals 0. Okay, and that was a consequence of the Bianchi identity. Okay, so in this lecture, we're now going to calculate G mu nu, Einstein tensor, in the weak field limit when G is eta plus H and H is small. And we're going to try to match it up with Poisson's equation. Del squared phi G is 4 pi G rho. Okay, by identifying H naught naught with phi. Now the argument is a little bit tricky, so we have to be rather careful, and in particular it'll turn out we're going to have to use both the 0, 0 and the ij components of this equation. Okay, so first of all, we use, so this is the equation we want to use to determine the constant. Okay, so we would like to fix a constant A by comparing with the Newtonian limit. Okay, so we have this equation as a proposal for our theory of gravity. So let's first consider the spatial components of one. Now, by assumption, we have Tij much less than T naught naught, right? That was the assumption that the pressure is negligible compared to the energy density. And for typical forms of matter, like a gas, the pressure depends on the square of the velocity of the particles. So this is the same as assuming the velocity of the particles is much less than the speed of light. But that's the assumption in the Newtonian limit. It's very valid for the Earth or for the Sun. The spatial stresses are much smaller than the energy density. So when we look at this equation, essentially the Tij we can neglect. And so this tells us that Gij is small, i.e. Rij is approximately 1/2 delta IJR. Okay, so if I just ignore the spatial spatial stresses, then I must have the Einstein tensor Ij components being small, and that means that the Ricci tensor spatial components must equal 1/2 the Ricci scalar. Okay, so that's a very useful equation. Now, the Ricci scalar is approximately equal to, well, of course, it's defined to be G mu nu R mu nu. And that's approximately, because G is approximately eta. Remember, this R mu nu will go like two derivatives of H mu nu, because G is eta plus H. Right, so R is already of order H, so there's no point in keeping the H in this G inverse, because that would be an H squared term. So you can replace that G with eta mu nu R mu nu. This is still first order in H. And this is equal to minus R naught naught plus, and then here I have RII, okay, because the ij components of eta are just delta ij. So I have delta ij times rij, and that's just the RII, the trace. But we have from here that the trace is 3/2 times R, minus R naught naught plus 3/2 times R. Okay, from this, let's call this dagger, from dagger. And so solving this equation, we see that the R00 is approximately 1/2 R. Okay, so I just pull that R over to the right-hand side, and I get 1/2 R, put the R naught naught on the left-hand side, and I get this equation for R00. And so it follows that G00, the Einstein tensor, which is approximately R00 plus 1/2 R, because eta mu nu is, eta 00 is -1, right? So that changes the sign here to plus 1/2, and this is approximately 2R00. So the left-hand side of the Einstein equation is just 2R00. Now, we already wrote down the Riemann tensor to linear order in this locally flat coordinate system. Let me bring this down. Sorry, this one. So that's the Riemann tensor. And it follows from this equation, let's call that star, R sigma rho mu nu, I'm just lowering the index now, is 1/2 H nu sigma rho mu minus H rho nu, comma, sigma mu minus H mu sigma, comma, rho nu plus H rho mu, comma, sigma nu. Okay, so all I did there is lower the index sigma. That produces a delta here, so this lambda becomes sigma. So that's the expression for the Riemann tensor to linear order in H plus order H squared. And all I want to do now is to calculate the Ricci. I need to calculate R naught naught. So R naught naught is just eta. I've got to contract the first and third indices. So So it's eta sigma mu r sigma rho mu nu. These indices are the rho and the nu. Okay, that's our naught naught. It's just the contraction of the Riemann tensor. That's a sigma. Now, r with 4 zeros is 0. Eta is only non-zero if sigma and mu are both 0. But r with 4 zero indices is 0 because r is antisymmetric. So this is r 0, 0, 0 with the minus sign, but that's 0. And then we have plus r, and then here we have I 0, because eta with two upstairs indices is just delta ij. And now I can just read that off from here. You see from this equation, I0 is equal to, remember we dropped time derivatives of h. We assumed h has no time derivatives. So here rho and nu are both 0. So that's gone because that's gone because h has no time derivatives. That's gone because rho is 0. And so I only have this term left. So I get minus 1/2. Sigma and mu are both I, and rho and nu are both 0. So I get minus 1/2 h00, comma I. And that's equal to minus 1/2 Laplacian h00. Okay, so the r00 is minus 1/2 Laplacian h00. And so now we're ready to plug back into the Einstein equation. Okay, so back to equation 1. Take the 0, 0 components, and we've got a times g00, which is approximately, using this equation, let's call that 3 daggers. So this equation is 2a r00, which is, now r00 is, we've just worked it out, is minus 1/2, so I've got minus a del squared h00. And this is supposed to be equal to 8 pi g, question mark, 8 pi g t00, right? But t00 is 8 pi g rho matter, because I'm using c equals 1. Okay, and we also remember that h00 is minus 2 phi g. The relationship between h00 and the Newtonian gravitational potential is just that h is minus 2 phi. And so what we have from this is that, so I have a 2 on the left-hand side, so I have a times d squared phi equals 4 pi g rho m. And so this is correct if a equals 1. Okay, so what we've shown is that this proposed Einstein equation, which is very easy to remember, 8 pi g T mu nu, this implies Poisson's equations in the Newtonian limit. Okay, so this is the Einstein field equation. I set the speed of light equal to 1. It's easy to put it back by units, bearing in mind T is an energy, and G is a... What are the units of G? The Einstein tensor. Metric is dimensionless, so what is this? L to the minus 2. Yes, so it's a length to minus 2. It's two derivatives acting on the metric. This is length to the minus 2. G is an energy. T is an energy. Put in the units, and you'll find there's a C to the 4th. So that was an exciting moment when Einstein realized he had a consistent proposal for the field equations. And these are arguably the most beautiful equations in physics. They show how energy creates curvature. Okay, and then according to the equivalence principle, the way the energy moves in a given curved background is entirely determined by its own equations. So you're free to put anything in there in the T mu nu, as long as it satisfies conservation of energy. And even if even if you only know it in a flat space, in Minkowski space, you can easily translate it into the form it should be in this equation just by changing eta to g and derivatives to covariant derivatives. Okay, so this equation really describes how energy bends space, the description of how energy responds to bent space is all contained in the equations for the matter. Okay, are there any questions at this point? Okay, I think you'll agree is that as ugly as all the algebra is to get here, the equation itself is very, very beautiful. What makes it even more beautiful is that it's true. Okay. So when Einstein wrote down the equation, there were practically 0 tests of it. This really was in the form of a hypothesis. But nevertheless, due to all the torture he had gone through in trying to derive it, he was completely convinced it must be correct. The first confirmation, I'm not sure we'll have time to do it this week, but the first confirmation was a well-known but fairly obscure fact known to astronomers, that the orbit of Mercury is not periodic. Okay, that Mercury is so here's the sun, and Mercury is going around in an ellipse. And according to Newtonian theory, if the sun is spherical, the orbit of the planet is an ellipse, and it's absolutely periodic. Okay, Newtonian theory, the exact solution of the equations, F equals ma, is an ellipse. But what was known by astronomers is that this ellipse is not periodic. The orbit of Mercury is not periodic. Actually, it precesses. And so it does this, right? So it's moving around at a very slow rate. And even in the 19th century, this was known to be not zero, and actually it was measured to be 43 arc seconds per century. Okay. It's a very, very gentle precession. And so what Einstein did is he worked out the field equations, he worked out the metric around a spherical mass. Actually, that was worked out by Schwarzschild, but Einstein knew it in the weak field limit, which is all you need. So he took the weak field limit of the metric. He solved the geodesic equation. He found the orbit is not exactly periodic, and he predicted this number almost exactly. Okay, with no free parameters at all. So that was pretty stunning confirmation. And then do you know what the second dramatic confirmation of general relativity was? Bending of light, yeah, bending of light, lensing, gravitational lensing. So yeah, this was Mercury. So this was confirmation number one. Confirmation number two was the prediction that when we look at light coming near the sun, it's bent, its trajectory is bent, so that the light appears to be, so that the galaxy or object behind the sun, which is being lensed, appears to be at the wrong position on the sky. And that angle is a deflection angle. So Einstein calculated it, actually got it wrong by a factor of 2 in his first paper. And then a couple of years later corrected that. There's a sort of trivial reason why he got the factor of 2 wrong. But then Arthur Eddington, who was the UK's sort of preeminent astronomer at the time and very mathematical, Eddington wrote the first book in English about general relativity, translating Einstein's ideas into sort of in more popular terms so that other scientists could read it. But Eddington also did an expedition to Africa, to West Africa, in order to see a solar eclipse. And during the solar eclipse, he watched the position of the stars next to the sun, and indeed he measured the bending of light. There was a very dramatic confirmation, I think it was in 1920 or thereabouts, of that prediction. People have since questioned that and wondered if Eddington maybe cheated a little bit on the data, but that is still not completely clear. But by now, these measurements are routine, and the theory works extremely well. And then general relativity sort of went dormant for a while, because it's very, very hard to test. These corrections to Newtonian mechanics are tiny. The principal importance of GR was in cosmology. And so people were developing models of cosmology like Friedman and so on. But still, there weren't many observational tests. There were very few observations in cosmology until much later. But at the moment, the situation is that that equation is absolutely the foundation of cosmology. You couldn't begin to do cosmology without that equation. And that equation, the meaning of cosmological observations is completely interpreted in terms of that equation and its framework. So this is now the foundation for cosmology. So every concept which the astronomers have, like redshift or Hubble constant or whatever, all of those concepts are just explained within or defined within the framework of general relativity. It's quite hard to imagine doing any science with gravity today without using general relativity. So what we're going to do now is study the prediction of gravitational waves, which was confirmed so excitingly 2 years ago, and which is still really the frontier for gravitational physics. Okay, so as soon as Einstein wrote this equation down, he realized that it would predict waves. Basically, if you throw away the t mu, just like with Maxwell's equation, we threw away the j nu, and we looked at the equation d mu f mu nu equals 0. Well, we'll do exactly the same in Einstein's theory. We'll throw away the stress energy and ask, are there any solutions to g mu nu equals 0? And because it's a second derivative equation, because locally it's going to look like Minkowski space with the metric will be Minkowski with a small fluctuation, it doesn't take a genius to realize that it's very likely to have wave solutions. In this case, it did take a genius to realize it, but it wasn't such a dramatic prediction that there should be gravitational waves. In fact, Einstein was desperately disappointed because he found there were waves, he wanted to measure them, and then he calculated the rate of emission of the waves, and it's so small that he thought it would never ever be detected. Okay, it seemed too ridiculously small, and then indeed it did take 1 century for those waves to be detected. Now, so the analogy with Maxwell, I hope you realize, is very deep. Maxwell's theory is the forerunner of GR. Maxwell's theory is much simpler. It's a linear theory, so the equation of motion is linear in f mu nu, much easier to solve. Einstein's equation is nonlinear and but therefore much, much richer. The set of solutions to Einstein equations is infinitely richer than the solutions to Maxwell's theory. Nevertheless, many of the same concepts work. So Maxwell's theory, we look at this equation to define gravitational waves, electromagnetic waves, right? Maxwell. So set J equals 0. And we already showed that this equation gives rise to electromagnetic waves. Let's discuss it from a slightly different point of view. Showed before that E and B propagate as waves. At the speed of light. So we expect exactly the same thing here. but this time it'll be the metric and the perturbation of the metric that'll go at the speed of light. But let's do it this time in terms of the gauge field, or the vector potential. F mu nu equals d mu a nu minus d nu a mu. And it's really this vector potential that's analogous to the metric. A mu is analogous to the metric. Because, why is that? Well, the metric is something which changes under coordinate transformations, so you shouldn't, the actual form of the metric should never be taken too seriously, because you can just change coordinates and change its form completely. Same is true of A mu. A mu is the vector potential in some gauge, right? So this is, so gauge transformations. A gauge transformation, A mu goes to A mu plus d mu theta, where theta is any function on space-time. This is analogous to g mu nu of x goes to g prime mu nu of x prime, which is dx dx prime dx dx prime g. Okay, obviously it's a more complicated transformation formula, but the principle is very similar. That these objects are useful calculational devices, but their specific exact form should never be taken too seriously. And so let's write Maxwell's equations in terms of this vector potential. And of course, what they look like. So the Maxwell, so let's just call that star. Star becomes d mu a nu, that's the first term. And then the second term is minus d nu d mu a mu equals 0. So that's Maxwell's equations in... So it's almost the wave equation. This term is the wave equation, but there's this funny term here. So it's not quite the wave equation. For A mu, in fact, what we can do is Fourier transform to understand the solutions of that equation. It's useful to Fourier transform So Fourier transform, it's a linear equation, so Fourier transform is always a good idea in a linear translational invariant equation. There's no explicit x's anywhere. So if we write A mu as the sum of epsilon mu e to the I k dot x. Okay, so this k dot x means k mu x, k nu x nu, which is k naught, which is minus k naught x naught plus k vector k dot x. Okay, so that's the exponent. So if I write A as this and plug that into the equation, actually let me call this, I'm going to call this A twiddle mu, that's the Fourier transform of A. So A mu of x is the sum over k of A mu twiddle of k. And then then we have k squared minus, I'll write it this way, k squared delta mu nu minus k nu k mu minus k mu k nu of A equals 0. Okay, so let's call this one star star. And so star star becomes this equation, right? So when I Fourier transform, I can just replace derivatives with ik. And so here I get minus k squared, and here I get plus k mu k nu. And I can combine these two terms by putting a delta mu nu in here so that this acts on the A nu to give A mu. And so this is the equation for A. This is a twiddle of K. And notice it's just an algebraic equation, right? This was a differential equation. This is just an algebraic equation. And this quantity here is just a matrix operator. Right, so I just have some matrix times A, or a twiddle, is 0. Now notice that the matrix has zero eigenvalues. Okay, in fact, A mu is a 0 eigenvector of this matrix. And in particular, this matrix, k squared delta mu nu minus k mu k nu, can you tell me a 0 eigenvector of this matrix? What is something that I multiply this by, expressed in terms of k, and obtain 0?
K mu.
K nu, right? So this times k nu equals 0. So that tells us that if I transform, if A nu tilde of k goes to A nu of k plus epsilon k nu, then this is still a solution. For all epsilon. Epsilon can be any function of and that corresponds to the gauge freedom. Okay, so obviously this epsilon, actually I epsilon, is just the Fourier transform of theta, this gauge freedom theta. So to solve the Maxwell equations, we can choose epsilon choose theta or epsilon to set k nu a, to set d mu a mu equals 0, which is the same as k mu a mu twiddle equals 0. And then what did we call it? This equation, star star, or this equation, let's call it 3 stars, or are solved if k squared equals 0. And this just means that k naught squared minus k vector squared equals 0, or k naught equals plus or minus modulus k. Okay, so the the energy of the photon is plus or minus the momentum, if you interpret the k as the k as the full momentum. Okay, so that's electromagnetism, that it has this gauge freedom. And in fact, we can use the gauge freedom to get rid of, so the way we usually solve electromagnetism, at least one way of solving it, is to use the freedom of shifting A by a gauge transformation, which is this or that, in order to, so use this freedom to set, so gauge fixing we set d mu a mu equals 0. This is called Lorentz gauge. And then you see that there is a residual gauge freedom, which is that a mu goes to a mu plus d mu theta with d squared theta equals 0. So even when you fix the gauge freedom, but you use up this freedom to set d mu a mu to 0, there's a residual gauge freedom because you can always shift A by something proportional to k that doesn't affect this condition because k squared is 0. Okay, so a mu twiddle goes to a mu twiddle plus I epsilon k mu with k squared equals 0. So what you see is this gauge freedom actually allows you to set two things to 0. You've got 4 components of the vector potential, 0, 1, 2, 3. One of them is set 0 in this condition. That's a single algebraic condition on a twiddle. That's the k mu a twiddle equals 0. But you still have a residual gauge freedom, which you can use to set another component of A to 0. The component along the k vector can be set 0. And that's how you go to 2 transverse modes. You naively have 4 modes for A mu, but the gauge freedom gets rid of 1, and this residual gauge freedom allows you to get rid of another one, so you end up with 2 propagating modes or polarizations of the electromagnetic wave. So we're going to do exactly the same thing for gravity, which is a little bit more complicated, but the principles are very similar. So for electromagnetism, a mu, 4 components, goes to 2 degrees of freedom, to propagating. Well, let's see. We do gauge fixing and what should I say? Yeah, let me just write it down. There's this. These are the physical propagating modes, physical modes. So in general relativity, we're going to have many more components. We're going to have 10 components of the metric, and we're similarly going to get rid of 8 of them. 4 by coordinate transformations. There are 4 coordinate transformations. And then 4 by residual gauge freedom, which will take us from 10 to 2. And gravitational waves turn out, just like electromagnetic waves, to only have 2 gauge-fixed degrees of freedom. Now, in GR, we need to pick a gauge. The first problem is to fix a gauge. Gauge freedom in electrodynamics was a choice we make to remove this freedom under A goes to A plus gradient of something, okay, because the physical quantities are the field strengths. So we need to choose some gauge, and in electromagnetism, the sort of a nice gauge, one of the possible gauges is this gauge, d mu a mu 0. This is obviously not invariant under A goes to A plus d theta, right? Because this equation changes by d squared theta. So you want to write down an equation which is not gauge invariant in order to fix the gauge. So what can we write down in general relativity which is not a tensor equation in order to fix the coordinates somewhat? Okay, so we have g mu nu, we have gamma, alpha, mu nu, we have various other things. What could we do to write down, we need to write down something which fixes the freedom to change coordinates. Actually, let me say a little bit more about this freedom to change coordinates. I told you already, it's this equation up here. So g prime mu nu is equal to g mu nu of x times dx dx prime dx dx prime. Now, if g is approximately eta mu nu plus h mu nu, right? So both these metrics are going to be close to flat space, and so g prime mu nu is going to be approximately eta mu nu plus h prime mu nu. And if x prime mu is equal to x mu plus epsilon mu of x, that's a small coordinate transformation, then you can me see, where is this? Okay, then you can see these equations imply h prime mu nu is equal to h mu nu minus epsilon mu comma nu minus epsilon nu comma mu. Okay, so I'll just leave it to you to check that. So what this means is I can do small coordinate transformations which will change the metric from having one h to another h, and the two h's are related by this formula here. Okay, so this is really analogous to this equation up here. A goes to a mu plus d mu theta. A has a single vector index, theta is a scalar. This is more or less identical, except the h has two indices and the epsilon is a vector. Okay, so that means that instead of a single gauge degree of freedom, this theta quantity in electromagnetism, we have four of them. It's one gauge degree of freedom for each mu. Okay, so epsilon mu corresponds to theta in EM. So we have 4 gauge degrees of freedom. Or 4 degrees of freedom in the gauge transformation, let's say that. 4 DOF in the gauge transformation. Okay, so in electromagnetism, we picked a gauge, d mu a mu is 0. One gauge condition to fix one gauge degree of freedom. What do we do in general relativity? I've got to write down something. I've got to write down 4 conditions because I've got 4 coordinates I could change. I need to write down 4 equations which fix the gauge. So what can I write down? I've got gamma, right? That's not a tensor. That's good for this purpose, not a tensor. I don't want to write down a tensor equation. What do I do with the gamma? There's too many equations there, right? This is 4, and this takes 10, so there are 40 quantities here. It's too many. I don't want to fix 40 things. I only want to fix 4 things. What can I do? That would be too many equations. I want only 4 equations.
Track at the bottom too?
Yeah, just write this down. There are 4 equations. Lambda 0, 1, 2, 3. Right? So these are 4 equations which are not coordinate invariant. And therefore fix the gauge. Okay, so there are 4 equations preventing you from changing coordinates. Okay, so this is a well-known gauge. It's called a harmonic gauge. So this is harmonic gauge. It's completely analogous to Lorentz gauge. It's called harmonic gauge, and I'll explain why. It's harmonic gauge because if we work out the Laplacian on a scalar quantity, we get something like this. See, the Laplacian on a scalar in 4D in a curved background is defined this way, where these are covariant derivatives. Now, the covariant derivative on a scalar is just the ordinary derivative because there are no indices on the scalar, so you don't need the connection. But this term generates a connection. So this gives you g mu nu d mu d nu phi minus gamma mu nu lambda d lambda phi. This is symmetric anyway. And this is equal to, in this gauge, in harmonic gauge, the second term vanishes. This is equal to g mu nu d mu d nu phi. Sorry, it's in the way. Okay, so this term vanishes in harmonic gauge, leaving me with only that term. Now, what this means in particular, if we regard the coordinate x mu as 4 scalars. See, x mu is not even a tensor. Dx mu is a tensor because dx prime mu is dx prime dx times dx. But x mu is not, doesn't transform. I mean, x mu goes to x prime mu, which is any function of x. It doesn't transform like a tensor at all. We can think about the coordinates as 4 scalars, and then it follows that box x mu, where this means the box acting on scalars, equals g mu nu d mu d nu x alpha in harmonic gauge. But 2 derivatives on the coordinates is definitely 0, because 1 coordinate will give me a delta, and 2 derivatives give 0 in harmonic gauge. Okay, and harmonic is always used to talk about something which satisfies box equals 0. If something satisfies box equals 0, we call it harmonic. It goes back to basically box being the wave equation, and harmonic things satisfy the wave equation. Because music is all about waves on strings. Okay, so in harmonic gauge, the coordinates satisfy this condition. So you can equally well write this equation as box x alpha equals 0. In this form, it's a little bit more mysterious. What am I doing taking box of coordinates? Coordinates aren't, but that's precisely why it's a good equation, because these coordinates are not tensors, and box x is not a tensor. In fact, box x is equal to this guy, which is not a tensor either, but there are 4 equations which fix which are 4 conditions on the coordinates. And these turn out to be very useful for discussing gravitational waves. Now, as we saw in electromagnetism, these conditions are not enough to completely fix the A mu, because I can still shift the A mu by something proportional to k, where k squared is 0, and I still satisfy the equations. So just like in electromagnetism, we'll fix 4 conditions, 4 coordinate conditions, and then we're going to have some residual coordinate freedom, and we have to fix those 4 freedoms as well in order to get the 2 physical propagating gravitational waves. So let me now write down the linearized Einstein equations, and we'll see how all this works. So the linearized Einstein equations So we start from g mu nu equals 0. Of course, g mu nu is nothing but r mu nu minus 1/2 g mu nu r. But if this is 0, then you can see immediately that r mu nu is 1/2 g mu nu r. And now I can multiply this with g mu nu. So multiply with g mu nu with upstairs indices, and we see that r is equal to, so g with g is delta mu mu, which is 4, the number 4. So this equation implies that r is 2r. Okay, and this implies that r equals 0. So in fact, if the Einstein tensor is 0, it follows the Ricci scalar is 0, and then it follows that the Ricci tensor must be 0. So these are the empty space, let's say, these are the Einstein equations with T mu nu equals 0 for T mu nu equals 0. You can write them as the Einstein tensor equals 0, but actually that implies the Ricci scalar is 0, and therefore the equations are just the Ricci tensor is 0. Now the Ricci tensor, we can just work out if g mu nu is eta mu nu plus h mu nu, then we just take our formula above for the Riemann tensor, contract a few indices, and we get r mu nu is 1/2 h lambda nu comma mu lambda minus h mu nu comma lambda comma lambda comma lambda minus h lambda lambda comma mu nu plus h lambda mu comma lambda nu. Nu lambda. Doesn't make any difference. Okay, so I just I had them somewhere. I think I erased them. But I had the Riemann tensor written out in terms of h, and we just contract some indices. That's what we get. This term is nice because it is box. This is box h mu nu. The other terms are kind of ugly. So let's reorganize that. We get minus 1/2 box h mu nu. And then we have minus h lambda nu comma mu lambda minus h lambda mu comma lambda nu, or nu lambda. And then we have plus h lambda lambda comma mu nu. So there's some kind of garbage here, which is very like this garbage term here in Maxwell. So here we had box A, and then we had the nasty term. So in general relativity, we have box h mu nu, and then we have a nasty term. And all we do to fix the gauge is get rid of the nasty term. It turns out that this is 0 precisely when I impose this harmonic gauge. Okay, so harmonic gauge is just h lambda nu comma lambda minus 1/2 h lambda lambda comma nu equals 0. Okay, so harmonic gauge obviously involves one derivative of the metric. And so I just invite you to work out that equation. So you can just take eta mu nu gamma mu nu lambda. This involves one derivative of the metric. There are three terms in here. Work out the three terms and re-express it as this. And then one can show that in this gauge, all of this vanishes. Okay, again, that's not difficult to show. Some quantity, a terminology which is used here is this is called transverse trace reversed gauge. So harmonic gauge for the linearized theory is called transverse trace reversed, also called TT gauge. Let me just explain the terminology. So I have h lambda nu. Okay, that's my metric perturbation. I happen to have raised one index and lowered the other. That's my metric perturbation. If I consider this quantity, h lambda nu minus 1/2 h, let's write it this way, alpha delta lambda nu. So consider this. So I take the h, I take its trace, which is the sum of these indices multiplied by delta. And this is called trace reversed. Can anyone tell me why this is called a trace reversed version of h? Because if I take the trace of this, right, it means contract the upper and the lower indices. I'm going to get h beta beta minus, and here I contract lambda with nu, I get a factor of 4, right? Trace of the identity matrix is 4, so I get minus 2 h alpha alpha, and so that is equal to minus h alpha alpha. So that means the trace of this is minus the trace of h. That's why we call it trace reversed. So just take the h, subtract off the trace with the right coefficient, so that the trace of the new guy is reversed. Transverse here just means that the 4 divergence is 0. So in other words, d by d lambda of h lambda nu minus 1/2, and then we'll take the trace here. Let's call it alpha so we don't get confused. Alpha alpha, this guy, times delta lambda nu equals 0. Here is exactly my trace reversed, h. Okay, so in this gauge, harmonic gauge, when you go to the linearized theory, is just the transverse trace reversed gauge. Yeah, sorry, I shouldn't have written on that one. Some of you probably can't see that. Write it out again here. So d lambda of h lambda nu minus 1/2 delta lambda nu h alpha alpha equals 0. Transverse means when dotted with the derivative, the 4 divergence vanishes, and trace reversed is this. So in this transreversed, this TT gauge, transverse trace reversed gauge, R mu nu is minus 1/2 box H mu nu. Okay, that's nice and simple. So the linearized Einstein equations are just box H mu nu is 0. And so obviously H mu nu travels like a wave. What we will show next time is that even though we've fixed the gauge, there's still residual gauge freedom. There are remaining coordinate, it's easy to see from here actually. What's the residual gauge freedom here? See, if box x is 0, if box x equals 0, and I go to some new coordinate system, so I say, let's go to x prime equal to x alpha plus epsilon alpha of x. What's the constraint on epsilon such that I'm still in harmonic gauge? That the box of epsilon is 0. So just like electromagnetism, I can do a gauge transformation by theta, but if I insist box theta is 0, I remain in Lorentz gauge. So you've got more freedom. You pick the gauge, and you still have more freedom. So we pick the gauge in GR. We still have freedom. It's still harmonic gauge. Harmonic. If box epsilon is 0. Okay? So we impose 4 conditions. We get to impose another 4 transformations. And that's how we go from 10 degrees of freedom in H mu nu. It's a symmetric 4x4 matrix. So it has a priori 10 degrees of freedom. We remove 4 by doing this, and we get to remove another 4 by doing those. And that's why there are only 2 gauge fixed propagating gravitational waves. So next time we're going to see that the photon, A mu, has spin 1. That is basically the properties of A mu under rotations. Okay, so A mu, electromagnetic wave is electric and E and B fields going along transverse to the direction of motion. If I do a rotation of space, they change, they rotate around, and shouldn't be a surprise that it is it transforms like a spin 1 object. The gravitons will transform like a spin 2 object, basically because it has 2 indices. And so we're just going to see that explicitly next time. Any questions? Yeah.
Is there like a gravitational cosmic microwave background?
Yes. Yes, there should be. So gravitons interact extremely weakly. Okay? So if the universe is full of gravitons, gravitational waves, they just travel right through us. Because if you think, what is a gravitational wave? It's just a distortion of the metric, right, by a small amount. The LIGO detector is capable of measuring H values down to 10 to the minus 21. That was their detection, right? The magnitude of H mu nu is 10 to the minus 21. So the wave that came from these 2 black holes merging changed your length by 10 to the minus 21 as it came past. It's not a big deal, okay? And so these waves interact extremely weakly with ordinary matter. They interact very weakly with everything, actually. So the way it works is that if you go back to the Big Bang, when the matter density was very high, the universe was very, very dense, then the gravitational waves would interact more strongly with the matter. And the reason is that each individual particle has very high energy. And, roughly speaking, you know that in gravity, energy sources waves. I mean, that's how Einstein equations work. So the only way to change a wave is for the energy to do that. So basically, near the Big Bang, the particles have enough energy to significantly interact with gravitational waves. That stops quite soon after the Big Bang. So at the very early universe, if we went all the way back to the Planck density, very high density, everything would be in thermal equilibrium, even the gravitational waves. So you'd have this hot bath of photons, gravitons, and everything. Then as the universe expands and cools, the energy of the particles goes down, and the gravity waves, we say, decouple. So they just travel freely. Ever since. What?
They kinetically decouple?
They just don't scatter anymore from anything else. So that's actually a fantastic thing, because it means that, they decouple when the energy of the early universe, the temperature, is not far below the Planck mass. I mean, it's about a factor of 100 below the Planck mass, basically the fine structure constant, I think squared. So maybe it's 10 to the 4 times below the Planck mass. So just below the Planck mass, they decouple. And ever since that time, these thermal gravitons would have traveled freely through space, and we should be bathed in them right now. Okay, so we can be fairly confident that the universe is full of this thermal gravitational wave radiation. Now, the really interesting thing is, can we detect it? Okay, so until quite recently, this seemed to be hopeless. The effect is just too small. These waves would do almost nothing to any interesting detector. But actually, last year, myself and somebody who visits Perimeter every week, Wei-Li Penn, we realized that in the very early universe, there were sound waves just from regular density perturbations. And these sound waves form shocks. We wrote a paper called Shocks in the Early Universe. And this is according to the most conservative, conventional picture you can imagine. No flaky, model building or whatever. There were shocks in the early universe. It turns out these shocks emit gravitational waves. So we're pretty sure that in the early universe, there were shocks in the fluid that emitted waves, and they could be seen today. The amplitude of the H, so LIGO is detecting about 10 to the minus 21 now. In the most conservative picture, the amplitude of the H coming from these shocks in the early universe would be about 10 to the minus 30. It's 9 orders of magnitude. LIGO has to be 9 orders of magnitude more sensitive to see them. But in various scenarios for the early universe, the sound waves would have bigger amplitude. In particular, people tried to explain the black holes LIGO saw by supposing that there were larger density variations in the early universe, which collapsed and made black holes. Turns out those would have emitted gravitational waves rather strongly, and they would have already been seen using something called a pulsar timing array. The wonderful thing about gravitational waves is they should be there on all wavelengths. The universe is practically transparent to them. And so if only we can see them, we can see everything about the universe, all the way back to the Planck time. Okay? So it's a great prospect. Right now, people are building detectors which are 1 centimeter. That's the smallest gravitational wave detector I know of. This guy was here. He's in Australia. He was here a few weeks ago. There was a whole workshop on this. And then, so that's the smallest one. There's a 30-meter gravitational wave detector in Fermilab called a holometer. Then there's LIGO, which is 4 kilometers. Then there is LISA, which is a satellite, proposed satellite to orbit the Earth, and that will be looking for gravitational waves of wavelengths 1 million kilometers. Okay, it's in space, and you look for these waves. And then, but right now we can measure pulsars, which are spinning neutron stars, and these have light year separations, and we use them as a big gravitational wave detector in the sky. So you can probe gravitational waves from centimeter up to many light years, okay, and using all of them, we can probe what happened in the Big Bang. So this is a completely new area of astronomy which is opening up, and it's pretty exciting. It's extremely difficult. I mean, the measurements are extremely difficult. You need to, just to detect the gravitational waves at all, it took basically 50 years of development from the 60s till today. That's what LIGO achieved. But now they've done it, this whole spectrum is opening up. So this makes me very, very optimistic that within, I don't know, 50 or 100 years, we will literally be making pictures of what happened at the Big Bang. So any theory of that will be tested. It's pretty unbelievable in a good way. I don't mean it's unbelievable. I mean it's believable, but it's pretty amazing. Okay, so next time we will do more on this.